Hi, I'm Vanessa Marin, and I did the scheduling, reinforcement, and business proposal for the project for the concrete canoe. Our main deliverables included the structural analysis report, the concrete mix composition report, the testing data sheets, the environmental impact report, and the business proposal. Another part of the scheduling included making agendas for all of our meetings. Our team held weekly meetings in order to get on the same page and explain our activities for the next week. If two people needed to exchange information, they would have a planned slot of time during the meeting. My weekly job was to create the agenda and to slot time for different team members to explain their concerns and give their update. I was also responsible for making schedule adjustments if we were veering from our original schedule. This slide shows how much a schedule can change during a project. We decided to use the steel mesh reinforcement with 4mm lateral by 5.4mm longitudinal diameter bars that are perpendicular to one another. The advantages of having steel reinforcement are: steel has a high ratio of surface area to weight, steel provides high tensile reinforcement, it's more rigid, and it helps with the stability of the canoe structure. The steel was chosen over the fiberglass due to the greater stiffness properties of the steel mesh and the higher shear resistance it has compared with the fiberglass.
Hi, my name is Brett Patterson. Working towards a more final concrete canoe mix for the ASCE competition, the team decided to come up with 3 different baseline mixes to batch in the laboratory. In order to make sure our concrete mix is strong enough, we set a goal of about 2,500 pounds per square inch for the compressive strength. We also need a tensile strength of about 300 psi, and we need a modulus of rupture which takes into account the bending stresses of about 300 psi as well. In order to ensure that the canoe will float, our unit weight of the canoe needs to be around the same as the water's unit weight, which is about 62.4 pounds per cubic foot, or PCF. Each of the 3 mixes differed in materials and proportions of the materials within the mix in order to analyze the beneficial properties of each mix and ultimately come up with a more final baseline mix for the concrete canoe. After calculating the batch amounts, the team was able to obtain the materials needed for the batches. As you can see around you, there were almost 15 to 20 of these different materials we needed to get. The problem with that was we had a very limited budget and we only had about 1 to 2 weeks to get all these materials. But we were able to do it, and we were able to batch with our 28 days of curing. Not only was obtaining the aggregates a difficult process, but you also need to make sure the diameter ranges of each one coincide with each other to create a continuous curve on sieve analysis. Here is the composite used in the final mix we decided. As you can see, it ranges from less than 0.1 millimeters all the way up to about 5 millimeters, which will ensure that the air voids will be minimized in the mixture.
Hi, my name is Jacob Batchelder, and I was the quality control technician for the Canoe project. The Argonaut team conducted 3 strength tests to determine which mix our final mix design would resemble. Although the canoe doesn't need significant compressive strength, the compression tests will be very useful in correlating the results with important design specs such as tensile and flexural strength capabilities. The split cylinder test determined the tensile strength capabilities of our specimens. The tensile strength was closely monitored because each trial batch contained various elements that theoretically aided in tension. The flex beam test simulated the bending conditions our canoe will be exposed to during competition. The flexural strength determined the effectiveness of all the structural elements considered in the mix design, for example latex or fiber reinforcement.
Mix 3 had the best overall results. However, despite a poor compressive strength, Mix 1 was up to par in tension, which we believe could be because of the addition of the PVA fibers. Also, we believe the addition of the latex admixture in mix 1 and 2 resulted in a better flexural strength.
Through testing and observation, we decided as a team that mix 3 would be the baseline mix with a few adjustments for the final concrete canoe mix. By observing mix number 3, it's slightly heavier than the other two, but it's got a nice smooth coat, air voids are minimized, and it is extremely strong. As you can see with this sample, this went through a split tensile test. The PVA fibers and the latex within allow this to stay together even though it's been crushed and has failed. For mix 3, we created 2 final mixes. We have the structural mix, which is very similar proportions to mix 3, but with the incorporation of the PVA fibers and the latex solids to increase its tensile and flexural strength. This is a mixture proportions table for the final structural mix that will be given to ASCE for further testing and use in construction for the concrete canoe. The patch mix is going to be used to fill in any air voids or any inconsistencies on the surface. We changed the proportions to having less cementitious materials and more aggregates to ensure that the patch mix is more workable and can fill in any spaces and create a more consistent, smooth surface on the outside of the canoe. Both the structural and the patch mix proportions can be seen in Appendix B of the final report.
Hi, my name is Brent Vandeveer. I did the structural analysis and the design drawing for the concrete canoe. Our canoe was analyzed using SAP 2000 version 9. To start off with the modeling, we used a shell element model. Started out with a barrel. It was kind of shaped like that, and pinched the model kind of towards the outsides to either end. Later models kind of look something like this. This is a 14-point model. We just kind of had to get a rough estimate of what the canoe is going to look like. Basically all the features you see here are actually what the canoe is going to look like this year. The shape was strongly dependent on our fluid analysis, which Elaine will tell you about next.
Hi, my name is Elaine Thornton. I did the fluid analysis and the environmental impact report and the organizational chart for the concrete canoe. One of the main considerations in determining the shape of the canoe was the effect of the drag force on the canoe as it's moving through the water. Skin friction drag, which is also known as the wall shear, is proportional to the surface area, and the pressure drag is proportional to the frontal area. Therefore, in designing the canoe, we decided we'd make the front slimmer in order to reduce the frontal area, which reduces the pressure drag, and we made the bottom flatter, which pulls the canoe out of the water, which reduces the overall surface area as it's moving through the water.
Alright, now we're going to talk about the canoe boundary conditions. This is one of the hardest things to come up with and one of our biggest challenges in successfully modeling the canoe environment. You can see from the picture here that we have both surface pressure and springs representing the hydrostatic force. The spring coefficient was determined using the force displacement of water and was distributed to 323 points along the bottom of the surface. We had to make sure that the springs were all equipotential to the surface, as well as the hydrostatic pressure. The water line is determined to be about 4 inches from the top of the rail. Extends all the way from the front of the boat all the way to the back, or from the bow to the stern.
In order to get the best chance of winning this canoe race, we need to minimize the total amount of drag force that's placed on the canoe in the water. The way we're going to do that is by using this aspect ratio, which is the length over the width should equal approximately 4. Looks to be a good compromise between the decreased surface area and the decreased flow of separation. By placing the heavier loads towards the back, the water line is adjusted, essentially adjusting the length of the canoe under the water, which maximizes the efficiency.
When doing our analysis on the canoe, we went in and took the heaviest loading, which was the 640-pound load with the 2 females and 2 males, the 4-person slalom, and we went in and modeled that in SAP. The maximum compressive stress you can see is located on the rails. The rails is where it really crunches up when we had the applied load in the middle of the boat. The tensile maximum point was located on the bottom of the boat, where the heaviest paddler in the middle was. So, it looks like, just based off of construction feasibility, we're going to go with a 0.75 inch hole thickness which has a maximum tensile stress of 180 and a maximum compression of 130. With the 3/4 inch, we are pretty much good to go with our current mix design. So that is the structural analysis.